like drought, like storms, like wildfire, so many things. So it doesn't mean, however, that all the extreme weather events are being made stronger or more frequent due to climate change. The role played by the climate change compared to other drivers of these extreme, like natural variability, like man-made drivers such as deforestation, etc., etc., all are having impact on these events as well as the climate change. And really, to check the footprint of climate change on the extreme events, it's a matter of and I mean the high-end research, in the sense that you need lots of accurate data sets as well as technical tools to get into all those things. So this webinar is an attempt to give we made sure that we have enough participants from the PG level students, MSc students, and also the researchers also, so that it will be a good platform to discuss all these issues. So I wish that in the whole event, the 2 days, everybody will interact with the experts who have spared their valuable time to be here with us. And I wish that this event will be a fruitful one from academic point of view. Thank you all. Over to Devalina.
Thank you, ma'am, for your kind words. Now may I request our guest and Dean School of Physical Sciences, Assam University, Silchar, Professor Chiraranjan Bhattacharjee, to address the web gathering. Sir, please.
Thank you. I suppose our Vice Chancellor could not join, no, in the session. Yeah.
Yes, sir. Yes, sir. No, sir, he is not
Fine.
there.
Anyway, Honorable Vice Chancellor, who couldn't join, Professor Dilip Chandranath and Professor Atri Deshmukh, faculties, scholars, students, resource persons, and dear participants. I note with great pleasure that the Department of Physics is celebrating the Silver Jubilee year with a bunch of webinars, one after another, addressing diverse topics for deliberation. Pandemic situation could not hold back the spirit. Rather, it provided an opportunity to accelerate organizing such academic discourses. I congratulate the entire department for this initiative. It is indeed a unique privilege for the university to welcome the esteemed invited speakers, Dr. Michael J. Mills, Dr. Roxy Matthew Call, Dr. M. Ali, and Dr. Amit P. Kesarkar, who will be sharing their expertise on the chosen theme in this two-day international webinar. Global climate change is a long-term weather patterns that characterize the regions of the world. Scientists today unequivocally acknowledge that the Earth is steadily warming up. Natural climate variability alone cannot explain this trend. Human activities, especially the burning of coal and oil, have warmed the Earth dramatically. The more of the trapped gases humans put into the atmosphere, the more the Earth gets warmer in the decades and centuries ahead. The impact of warming can already be observed in many places, from rising sea levels to melting snow and ice to changing weather patterns. Climate change is already affecting the ecosystems, freshwater supplies, and human health. We are witnessing prolonged periods of excessively high temperatures, heavy downpours, storms, wildfires, and in some regions, severe floods and droughts. Although climate change cannot be avoided entirely, perhaps the most severe impact of climate change can be avoided by substantially reducing the amount of heat-trapping gases released into the atmosphere. However, the time available for beginning serious action to avoid severe global consequences is really very short. The most daunting problem of climate change is to recognize the trends and draw action plan for implementation. Climate shocks and stressors such as cyclones, floods, droughts, changing rainfall patterns, and extreme temperatures are some examples of uncertainties that we are confronted with today. Current scientific researches highlight serious worldwide adverse health outcomes related to climate change. A changing climate leads to change in frequency, intensity, spatial extent, and time of weather and climate extremes, and can result in unprecedented extremes. I'm certain that deliberations in the webinar will reflect on such vital issues, recognizing newer directions, generating newer cues for further research. I particularly would like to call upon the students, scholars, and young researchers to take note of these. Wishing the webinar a great success. Thank you all once again.
Thank you, sir, for your precious words. May I now request Professor Ashok Kumar Sen, the chairperson of the organizing committee, to say a few words. Sir, please.
Yes, am I audible?
Yes, sir, you are.
Okay, good morning, everybody. This is very nice to see the gathering. We have experts from outside the country. We have experts from within the country, and our students, our faculty members, people working in atmospheric science, meteorology, and allied areas. I think we have a lot of things to learn from this meeting, and I look forward to all these deliberations. So I will not waste much time. Let the speakers take their turn one by one. And to begin with, we have Dr. Michael J. Mills. So I look forward to let this be started. Thank you very much.
Thank you, sir, for your valuable words. Now I would like to request Dr. Utpal Sharkar to propose the vote of thanks. Sir, please.
First of all, a very good morning to all of you. I would like to thank all the speakers, Dr. Mikhail J. Mills, Dr. Roxy Matthew Call, Dr. M. Ali, and Dr. Amit P. Aserkar for accepting to be a part of the international webinar. I would like to thank all the participants also for attending this webinar and the organizing committee members of this conference. I should thank the chief guest and Dean of Physical Sciences, Assam University Silchar, Professor Chiraranjan Bhattacharjee for his valuable words. I would like to thank Chairperson Chairperson Professor Atri Deshmukh, who is organizing this webinar, and our guest, Professor Ashok Kumar Sen, for chairing this session and his words. I would like to thank all the faculty members, including the staff, research scholars, students of the department for their help in different ways. Finally, I would like to thank everyone who is directly and indirectly extending their help and support for this webinar. I am sure that all the participants will be benefited throughout through this conference. I wish this conference a grand success. Thank you all. Over to Devolina.
Thank you, sir, for your words. Formally, our inauguration program is over with this. Now we are entering into the first technical session. And before that, I request all the participants to put your question in the chat box after the completion of the lecture, and please do not turn on either audio or video. Now I am supposed to hand over the session to the convener, Professor Atri Deshmukh, for introducing the first speaker of the webinar. but I think there is some
Yeah, I'm here.
problem. Ma'am is
No,
not
there's no
here.
problem.
Oh,
I'm
okay,
here.
ma'am. Okay,
Yeah.
ma'am. Okay, ma'am. So I am handing over the session to the convener, Professor Atri Deshmukh, for introducing the first speaker of the webinar. Ma'am, please.
Yeah. So, Debolina, thank you. A very good morning to you all again. We are going to start the first technical talk of this webinar series. So, our first speaker is Dr. Michael J. Mills, and he is the leading expert in the field of microphysics of stratospheric aerosols, stratospheric ozone chemistry, and climate. So he is like working in modeling chemistry, dynamics, and aerosol microphysics in the middle atmosphere for over almost 20 years. He is right now he is a project scientist in National Center for Atmospheric Research, USA. It's almost for 10 years he's there, and he is also the community liaison for the whole atmospheric community climate model. And he has almost 50 plus publications in different leading areas. And one of the interesting result I would like to share that if there is a regional nuclear war between India and Pakistan, that can produce a global ozone loss of 20 to 50% over populated areas, which is an unprecedented level in the human history. So that is one, just to share the one of his works. And I request Professor Mike, actually I'm very thankful that you have spared your valuable time for us, for the students who have joined the webinar. So I request Dr. Mike to start without wasting further time. We are just reaching 9. We should start. So over
Thank
to
you.
Dr. Mike.
Thank you for that introduction. I realize now I should have given a talk on maybe a different subject, on the nuclear winter. But I'm going to be talking about volcanic eruptions and global climate and ozone loss. And maybe if we have time at the end, a little bit about geoengineering. This is a beautiful sequence of photographs taken by an astronaut on the International Space Station of a volcano erupting in the Kuril Islands between Kamchatka and Japan in 2009, the Sarychev Peak. And you can see a lot of different things happening here with the condensation of the vapor around the ash as it's rising, and the eruption has punched a hole in the lower stratus clouds, and lower down you can see pyroclastic flows flowing down the flanks of the mountains. And this is one of the eruptions that had some significant impact on the temperature of the planet. It's included as a number of small to medium-sized eruptions that have happened since the year 2005, in contrast to the previous 10 years when there were few. And so I'm going to begin by talking about the year without a summer, which was the year 1816. It followed the eruption of Mount Tambora in Indonesia in April of 1815, which was perhaps one of the most explosive volcanic eruptions, depending on how you measure it, of the last 10,000 years. On the island where it occurred, only 26 out of 12,000 people survived. The earthquake and the eruption killed 90,000 people in the region, and 200 miles around the volcano experienced 3 days of total darkness from all the material that was put up into the atmosphere. And this figure shows the mean temperatures in June in degrees Fahrenheit in Connecticut, which is in New England, which is the northeastern part of the United States, And you can see the following year, 1816, is a dramatic decrease in the mean temperature in the middle of summer. And as well as the year after that, 1817, which really stands out in this record of about 70 years of temperatures. There's a book about this eruption, a really great book by Gill and Darcy Wood called Tambora, the Eruption That Changed the World. And in it, he says that for 3 years following Tambora's explosion, to be alive almost anywhere in the world meant to be hungry. In New England, 1816 was named the year without a summer, or 1800, and froze to death. Germans called 1817 the year of the beggar. Across the globe, harvests perished in frost and drought, or were washed away by flooding rains. Villagers in Vermont, which is also in New England and northeast US, survived on porcupine and boiled nettles, while peasants in Yunnan and China sucked on white clay. Summer tourists traveling in France mistook beggars crowding the roads for armies on the march. And I should say this eruption happening in April of 1815 was about the same time as the Battle of Waterloo. So it was Europe was coming to the end of many years of the Napoleonic Wars, and this eruption had a big impact on their ability to recover and feed themselves after this period of wars. This shows the northeastern U.S. and New England, the line of snow that happened in the middle of summer in June in 1816. It's not normal to have snow in summer in this region, but it extended well into the United States here. This shows 3 different states in New England in the US, and the impact on the growing season, which was reduced from the normal period of about 140 to 180 days in the year down to about 60 days or 70 days, which had a big impact on the ability to grow crops. They don't grow fast enough to produce food. The crop failures in New England caused prices of wheat and corn to go up. On the other hand, prices of meat, pork, and beef went down as people slaughtered livestock to avoid starvation. There was famine in Europe as well as in Bengal and India. In France, there were riots. And this also coincided with sparking people to leave northern part of the United States in New England and move westward towards what's now the Midwest part of the United States. At the time, it was the western frontier. So states like Vermont in the Northeast had population losses. Their population was set back by 7 years, and the population decreased by 8%. It spurred the development of a major canal across the state of New York in 1817 to improve transportation to the interior of the US. Also, sadly, this was the first cholera pandemic following this eruption. It's the first time it's believed that cholera spread outside of India, and this is thought to be due to disruption of the Asian monsoon, which caused unusual patterns of dryness and then a lot of wetness. And we see the years following 1817, cholera started spreading to other parts of the world, Africa, Europe, and North America. This is a photograph of an eruption of Mount Pinatubo in the Philippines in 1991. This a few days after this photo was taken, there was a larger eruption of Mount Pinatubo. We don't have great photos of that because it happened in the middle of a typhoon hitting the Philippines, but it was that eruption a few days after this one that put 10 to 20 million tons of sulfur dioxide up into the stratosphere. And here we see the temperature record, the global average annual temperature over from 1880 to the present. And following Mount Pinatubo, as well as some other eruptions that are shown here throughout that record, we see short-term decreases in temperature. And that's because of all the material that was put up into the upper atmosphere. So we'll talk about why that happened. How volcanoes cool. Basically, the sulfur dioxide that they put up turns into sulfuric acid, which forms particles with water known as aerosols, which are tiny and shiny droplets that remain suspended in the upper atmosphere, in the stratosphere. And in the stratosphere, there's no weather, there's no rain. So it remains up there for years until it's removed by the atmospheric circulation. And so these tiny, shiny particles scatter sunlight coming in back out into space, so less of it reaches the surface. And the result is that the surface temperatures go down. That's shown in this figure here, the reflection of shortwave sunlight. But there are other effects as well. And the aerosol can also absorb long-wave radiation. And most of the long-wave radiation is coming back up from the Earth's surface because the Earth is not as warm as the sun. The energy is lower, and we have longer wave radiation. And that causes the region where the aerosol is up in the stratosphere to heat up while the surface is cooling. And the situation is even more complicated than that when we start to look at the impacts of these aerosols on clouds. And there are many uncertainties as to what all the impacts are. But for example, one important effect is that adding aerosols can cause cloud droplets to become smaller. And when they're smaller, they become more effective at scattering sunlight. And so that can cause them to be more reflective and reflect more sunlight out into space. But that's talking about clouds in the lower part of the troposphere. If we're talking about higher clouds, such as cirrus clouds made of ice, well, then we really don't know exactly what's going on, but we know that cirrus clouds actually absorb and can warm this. They absorb the long-wave radiation and can warm the surface. And so figuring out the effects of aerosols on those is important, especially if we're going to do something like geoengineering. This is a figure of a database of volcanic eruptions that we have developed based on satellite observations since 1979, when we had the first satellite retrieval of volcanic sulfur dioxide. And these eruptions are shown with the latitude on the left vertical axis from the North Pole at the top to the South Pole at the bottom, and versus time, the year of the eruption. The size of the circle is an indication of the amount of energy of the eruption, known on the scale called the Volcanic Explosivity Index, from a scale from 0 to 6 here. The color of the circle is a measure of the amount of sulfur in the eruption. And so if we look at the left side, we see El Chichon erupted in 1982, and Mexico had a great deal of sulfur, whereas Mount St. Helens, which happened in 1980 in the United States, had about the same amount of energy as El Chichon, but less sulfur. And so it had less of an impact on the climate. And there in 1991, we see Mount Pinatubo, which had probably the largest impact on sulfur going into the stratosphere and climate, perhaps of the 20th century, and certainly of the last, during the satellite era since 1979. But we notice a few things, patterns going on here. Many people talk about these two periods following the El Chichon eruption in 1982 and Mount Pinatubo in 1991. And then that was followed by about 10 years in which there were not really any big eruptions. There were some small ones. And so we call this a volcanically quiescent period in which the stratospheric aerosol returned to a low level. But then after 2005, we see an increase relative to the previous 10 years, an increase in these small and moderate sized eruptions happening. And this had an impact on, as we'll see, both the climate and the ozone layer. And if we look, if we remove those big eruptions, Chichon and Pinatubo, and look at only the small and moderate eruptions, we look by decade. We see in the 1980s there were 6.3 teragrams of SO2. In the 1990s, 1.4 teragrams if you take out Pinatubo. In the 2000s, there were 5.3 teragrams of SO2, and then 2010 to 2015, 3.7 teragrams of SO2. And so we see that this volcanically quiescent period following Pinatubo was unusual in that over the period of the satellite record, most of the time there have been more of these small and moderate eruptions that are significant. And that's important because they're often ignored in climate models. And so my colleagues and I have been looking at the impact of small to moderate eruptions that have happened since 2005 on the global climate change, as well as the recovery of stratospheric ozone. And we've been using a model that was mentioned in my introduction. It's the Whole Atmosphere Community Climate Model, WACCM or WACCM, which is a component of the Community Earth System Model, or CESM. And WACCM is a high top model in that it extends from the Earth's surface all the way to basically the edge of space. The lower thermosphere extends up to 145 kilometers roughly. And it includes interactive chemistry to calculate stratospheric ozone levels and interactive dynamics as well. And this is just a sketch of how high WACCM goes, the red arrow showing it going to 145 kilometers in comparison to our standard atmosphere model that we have at NCAR and CSM, which is the community atmosphere model, which only goes up to 45 kilometers, which is in the middle of the stratosphere. And so by going up higher, we're able to capture more of the interactions that happen to affect the circulation in the stratosphere and what we call the middle atmosphere. So this is just a sketch of the chemistry that's going on that develops these aerosols in the stratosphere. And the volcanoes put in this SO2, sulfur dioxide, and but there are other sources of SO2, including this molecule OCS, which is also called carbonyl sulfide, which is always putting in a pretty steady amount of sulfur into the stratosphere. It comes from the surface and doesn't break down until it gets up into the stratosphere. And then the SO2 oxidizes through various pathways to form sulfuric acid, H2SO4, in gas form, and that consolidates with water droplets to form these aerosols, which we call sulfate aerosols, which are a solution of sulfuric acid in water. And so in the model, we include a number of processes in chemistry and microphysics. This is the chemical pathway to the development of sulfuric acid. But then we have the gas to particle conversion or nucleation, as I mentioned, where water and sulfuric acid molecules get together and form these tiny, shiny particles. And then the particles can grow by collecting more water and sulfuric acid molecules. They can grow by colliding with one another in coagulation. And as long as they're tiny, they're suspended by the atmosphere, the energy of the molecules around them. But once they grow to certain sizes, they start to fall more rapidly through the air, and that's called sedimentation, which can ultimately remove them from the atmosphere. This is satellite observations of before and after the eruption of Mount Pinatubo, which happened on June 15th, 1991. So in the upper left figure, we see the non-volcanic background level of stratospheric aerosol as observed by this satellite. And then in 1991, we see, after the eruption happened in the Philippines, this aerosol circled the globe around the equator in the tropics, because of the zonal winds transport air in the stratosphere rapidly in east and west directions. And then after that, it began to spread from the equator towards both poles. That's how the air moves in the stratosphere. It rises up from lower altitudes in the tropics, and then it spreads out to the North Pole and the South Pole from there. And then, so in 1993 and 94, we start seeing reductions in the aerosol, because some of it has fallen out and some of it has been transported to high latitudes, where it re-enters the troposphere, and then the troposphere, being the part of the atmosphere where we live, has a lot of weather that can wash it out, whereas while it's in the stratosphere, it tends to stay there for years. So this is a simulation of the eruption of Mount Pinatubo happening in the Philippines in our model, and you see it spreading east and west, and then more slowly north and south to the poles. And then 2 months after the Pinatubo eruption, there was another eruption happened in Chile, which was pretty significant as well. And it's starting to reduce in the years that follow. Now, this is an animation of a number of eruptions that have happened starting in 2008. Whoops. So we see this eruption of Kasatoshi happening in the Kuril Islands, followed by the next year Sarachev Peak in the similar area. Actually, Kasatoshi was in the Aleutian Islands. In 2011, we have 3 eruptions happening within a month, spanning the globe from north to south, and also including in the tropics. And then this eruption in 2014 staying largely in the tropics. And then finally in 2015, this eruption of Calbuco, which happened in southern Chile. And we're going to talk about this because this helped to produce the record large ozone hole that was seen that year. So in order to validate our model, we compared to satellites, and this is just showing that our amount of sulfur gas that our model is showing following the eruption of Pinatubo, for example, in 1991, the sulfate is comparable to that which was measured by satellites, the high resolution sounder, HIRS, infrared sounder satellite, as well as some other instruments, MePass, which measures carbonyl sulfide. And looking at some of the MePass sulfate and SO2, they're actually, this is unpublished data that has some issues with detecting lower levels. So that's can account for some of the discrepancies that are seen there. So as I mentioned, the circulation in the stratosphere is one in which air enters from the troposphere, the lower part of the atmosphere, into the stratosphere in the tropics, where there's ascent from convection and gravity waves pushing the air upward there, and then there's transport to higher latitudes. And then this black line we see here is the boundary between the troposphere and the stratosphere. We call it the tropopause. And you notice it bulges up higher in the tropics, and it's lower in higher latitudes towards the North Pole and the South Pole. And there's this region called the lowermost stratosphere, which exists at mid and high latitudes, where the air tends to reside still in the stratosphere, but it's difficult for satellites to actually detect the aerosol there because of interference from cloud tops, some satellites, that is. And so some models used stratospheric aerosol from satellites to prescribe the amount that was in the model, whereas we take an interactive approach, and we have produced this simulation here showing the amount of stratospheric aerosol on the top from 1990 to 2014, and I've labeled the various eruptions that are happening throughout that period. And on the bottom is where we are taking a simulation without volcanic eruptions, and we're just subtracting off the non-volcanic aerosol so that you can see the impact of volcanoes through the full depth of the atmosphere there. And we validate the model also by comparing to LIDARs, which are laser beams that we shoot up from the ground. And they can measure aerosols very well in regions where satellites have trouble. And so we see the comparison to this Gaystock LIDAR in Germany. After Pinatubo compares well to our model, the black line, and then this in more recent years, we're comparing to this LIDAR in Siberia in Tomsk in yellow. And in contrast, I'm going to show you here in blue and green, these are satellite-based climatologies that had been used by some models previously. And we can see some differences between that and what our model calculates. And in particular, in the period since 2005, both of those climatologies are missing a good deal of the aerosol that resides in the lowermost stratosphere. And so they weren't able to produce as much stratospheric aerosol, which is important for climate as well as the ozone layer. This is just showing, we're comparing to LIDARs at various latitudes from 79 north in Scandinavia, down through the Hawaii at Mauna Loa, and then the southern hemisphere in New Zealand in Lauder as well. And the model is the simulations in red and blue, which have a slight difference in how they're run, but are both very consistent with these observations from LIDARs. So another thing I mentioned is that stratospheric aerosols can heat the stratosphere by absorbing the long-wave radiation. And that's something that is observed as we see in the black lines here. These are temperature anomalies that are measured from radiosondes at different altitudes here. And you can see after the Chichon eruption in 82 and the Pinatubo eruption in 91, these spikes in temperature due to the heating of the stratosphere from the volcanic aerosols. And our model is shown in red, very well reproducing this heating phenomenon that's been observed. You'll also notice over the long term, the temperatures in the upper altitudes are decreasing. This is due to greenhouse gases, so largely carbon dioxide. Although greenhouse gases warm the troposphere where we are in the surface, they have a radiative cooling effect in the upper atmosphere. And so this is more evidence of the effects of greenhouse gases. And our model reproduces that as well. This is a comparison of the radiative response in the model to that which was seen in a satellite, the Earth Radiation Budget Satellite, which is the black line here. And so the top one is the absorbed shortwave radiation, which is basically the absorbed amount of sunlight seen by a satellite. And then in the red, we have our WACOM simulation with volcanic eruptions, and blue without volcanic eruptions. And so we can see after the eruption of Pinatubo, this big decrease in the shortwave due to the eruption, which you don't get when you run the model without volcanic eruptions. Similarly, the outgoing long wave decreases due to the absorption by the stratospheric aerosols in the red simulation. And you can see when you run without the eruptions in blue, you don't get the same decrease. And the bottom is just the difference between the two, which is a measure of the impact of these eruptions on the total amount of energy that the Earth absorbs. So let's look at the impacts of these small to moderate eruptions on surface climate. First of all, this is simulations from some of the models that went into the coupled model intercomparison project version 5. It's a measure of the total amount of heat content in the ocean in these models, which you can see increasing due to global warming in recent decades throughout the 20th century, in fact. But we also see that following some of these big eruptions, there's a significant reduction in the heat content in the ocean, and the light blue is the upper level, the shallow ocean, which absorbs most of the heat. And then the other colors are deeper in the ocean. And so the first, I think, 2 meters of the ocean has as much heat capacity as the entire atmosphere. And so this is important thermal inertia for climate change. This is from our simulations of just looking at the short wave and the long wave reaction to volcanic aerosols. The short wave scattering in the blue shown as a reduction following the 1982 and 1991 eruptions, and also following the more recent small and moderate eruptions since 2005. And the long wave has an opposite effect on surface climate. The absorption of long wave radiation in the stratosphere can actually warm the surface a little bit. So the net effect of the forcing is the black line, which is the difference between the blue and the red. And again, these are from our simulations. So we see following Mount Pinatubo, we have this quiescent period, and then since 2005, these small magnitude eruptions. And so using our model, we're able to calculate what is the radiative forcing of the small amount of aerosol during this quiescent period in 1999 to 2002. And we calculated negative 0.04 watts per square meter, which is radiative forcing is a measure of impacts of climate change. And then looking at what happened from the period 2005 to 2015, we see 3 times as much negative forcing or cooling, 0.12 watts per square meter negative. And so the difference between those two is 0.08 watts per square meter, which is in agreement with some previous studies that have been done. And interestingly, we can compare it to the amount of warming over the same period from carbon dioxide increases, which is about 0.25 watts per square meter. And so about 1/3 of that warming was offset by these volcanic eruptions, or about 30%. So these volcanoes should not be neglected when we're predicting climate change. Of course, we can't know what volcanoes are going to do in the future, but they can explain when global warming doesn't proceed as quickly as expected in the absence of eruptions. And this is a validation of our model's ability to predict the surface temperature shown in this black line compared to range of observations as the gray shaded lines. And we're comparing here to this green line, which uses this older satellite climatology in which these small eruptions since 2005 were neglected entirely. And so we can see that when we include these eruptions, we get closer to the pattern of warming that is observed, whereas the green line shows too much warming because it doesn't have the those eruptions. And the difference is about 0.07 degrees Celsius. So eruptions can also affect the stratospheric ozone loss and recovery. Ozone is what defines the stratosphere. It's a molecule formed from three atoms of oxygen in the upper atmosphere, and it causes heating because it absorbs ultraviolet light. And so it causes this layer called the stratosphere, in which, in contrast to the troposphere, where we're close to the surface, when you go up in the troposphere, temperatures drop pretty quickly. In the stratosphere, as you go up, temperatures increase, and that's because it's being heated by the absorption from the ozone molecules, the absorption of ultraviolet. And once you get above the ozone layer, you get into a region where the temperature starts decreasing again, and that's called the mesosphere. So this region where we have warm temperature over cold temperatures is a very stable region, and that's why it's stratified, and you don't get a lot of turbulence or weather going on in the stratosphere in contrast to the troposphere. Ozone, of course, also protects us from ultraviolet light, and so it was alarming when in 1985 it was reported that there was this ozone hole over Antarctica, which was entirely unexpected. About 50% of the total amount of ozone in the atmosphere was missing in the months of September, October, November, for a number of years, starting in about 1980. And there are interesting stories about how satellites missed that, but people on the ground, there's a guy from the British Antarctic Survey who first reported it, named Joe Farman. The reason was because of chlorofluorocarbons, which we use in air conditioning and refrigeration, as well as many other purposes. So in order to get an ozone hole, you need to have these chlorofluorocarbons, which rise up into the stratosphere and break down and release chlorine and bromine atoms and molecules. You need cold temperatures because you need, in Antarctica, it's the coldest region, one of the coldest regions of the stratosphere. And it's so cold that there are clouds of ice that form in the stratosphere, polar stratospheric clouds. So there they are, that's what they look like, mother of pearl clouds. And there are reactions that happen on those ice particles when the temperature is cold and when the sunlight comes out to allow photochemistry to happen. And so this is a paper from way back in 1996 showing the decrease in ozone over Antarctica here as these little symbols, the asterisks and the diamonds. And then we have some model calculations in which in the dashed lines, we have basically no volcanoes, a constant amount of aerosol, whereas the solid line has the observed level of aerosol due to these eruptions, largely from El Chichón in 82 and Mount Pinatubo in 91. And so this model was very well able to reproduce these decreases in ozone from what you see on the bottom, the increasing chlorine, and then the variability in the aerosol due to the volcanic eruptions. And that's because these aerosol particles help to form more of these polar stratospheric clouds, ice particles, and you have more of what we call the heterogeneous chemistry, which enables the ozone hole to form. So there's these two eruptions. This is more recent with our Wacom model, and this is showing a similar thing where the observations from satellites are seen in the black here, and the others are various forms of our model. And particularly the purple line is when we're using a model in which we're nudging to get the right temperatures and winds that were observed. We really reproduce this year-to-year variability very well in ozone. This is from a paper in 2016 called The Emergence of Healing in the Antarctic ozone layer, and it's a measure of the amount of ozone that was lost due to volcanic eruptions from 1999 until 2016. And we note a couple of the big ones, Pujehue Cordon-Pallier in the year 2011, which is in southern Chile, and then in 2015, this Calbuco eruption, which produced this really big ozone loss seen there. And this other paper by Diane Ivey calculated that this volcanic eruption was really instrumental in producing this record large ozone hole in 2015. This is just showing that there are also effects on outside of Antarctica on the global amount of ozone we see was reduced after the Pinatubo eruption, and we've reproduced this in our model as well, following both the Chichon and Pinatubo eruptions. And now I'm running out of time, I think, but maybe I'll just mention that we've used our models for geoengineering, which is this idea that we could try to offset global warming by doing artificial volcanoes, because global warming is accelerating. Millions of people are suffering, and there's going to be more pressure to try and do something about it. Although the only real solution is cutting carbon emissions and eliminating carbon emissions, and perhaps even trying to find a way to remove carbon dioxide from the air, which is going to be very difficult and expensive. But if we were to try and offset global warming, the cheapest and easiest way in a short term would be to put particles in the stratosphere the way volcanoes do. And one way we could do that is with a feedback mechanism. This is just a concept of adjusting the temperature when you're in a shower in a hotel that you're not familiar with. You use feedback, where you adjust the temperature dial and see what it's like, and then adjust it some more. And so we use this approach in our modeling to try and control 3 different climate parameters: global average temperature, the equator to pole temperature gradient, and the interhemispheric temperature gradient. And in fact, we're able to do that in theory in our model by putting different amounts of sulfur at different latitudes. And this is just a movie showing what that looks like. This is the year before we start geoengineering. This is natural amounts of aerosol in the atmosphere. And then you'll see in January, we start injecting aerosol in the stratosphere, first in the northern hemisphere, and it starts filling up the northern hemisphere with aerosol. And then the model the next year decides to start also doing it in the southern hemisphere. And this continues until we have an aerosol covered globe. This is just another look at that, but I'll just mention that briefly, and I'll put up my summary here and ask for questions.
Thank you so much, sir, for this wonderful lecture. So in the chat box, there are so many questions. So I will put some questions before you, sir, if you allow. So.
Yes.
Okay. So the, one question from Trishanu Bonik. He's asking that what are the short-term and long-term impact of volcanic eruption on local convective activities like thunderstorm, lightning activity, etc.?
So the effects I look at are more global effects. So volcanic aerosols in the stratosphere, reducing the amount of sunlight that gets in, which reduces the total amount of energy. And so it would be a reduction in the amount of energy to form things like thunderstorms. But perhaps you're asking about there are things like lightning that happen in the plume of a volcanic eruption. And there's some beautiful photographs of that, just due to the ash particles, which cause charge separation as the eruption happens. And so that's a cloud that can form from an eruption, similar to what you see when there is a large wildfire producing a lot of smoke. As actually, I saw one of those on Monday near here. There was a very large wildfire, and fortunately, the temperature changed very dramatically the next day, and we've had snow on the ground here. But anyway, that's just one of the effects of global warming. So I guess we'll go to the next question.
Okay, so next question from Raju Mandal. He's asking that given that anthropogenic factors don't affect volcanic eruption or its effect on climate change, can it be a part of policy discussion or debates on climate change?
Yeah, well, in order to understand the anthropogenic climate, we need to understand natural variability. And volcanoes are one of two of the largest sources of natural variability in climate, the other being the solar variations. And so if we don't understand those, we can't be confident in our climate models. For example, there was a lot of concern about climate models predicting much more warming after 2005 than was actually observed. And part of that is due to these volcanoes, which cooled temperatures for a number of years. And of course, the other part of policy that is related to volcanoes is geoengineering, and whether we would ever want to try and do something like that on purpose. Okay, next question.
Okay, sir, the next question is the ozone hole found in Antarctica at 1985, but there is no pollution on Antarctica. So why the ozone hole became there? Also, the ozone hole should become in the cities which are highly polluted, but that is not happened. Why? One question from Vijay.
That's a great question. When we think about pollution, we think about smog in cities. And that's one type of pollution that exists very close to the sources of the pollution because there's photochemistry happening there that causes it to not last very long, to be short-lived. But there's another type of pollution. Carbon dioxide is one. Carbon dioxide will remain in the atmosphere for thousands of years. And chlorofluorocarbons are another of this long-lived type of pollution. These are very complex man-made molecules that started being produced in the 1920s, and they've been used largely for refrigerators, air conditioners, but we found more and more uses for them. And so they really increased in their concentrations in the atmosphere over the 20th century. Unfortunately, not only do they warm the atmosphere, but once they get up into the stratosphere above the ozone layer, that's where they break down from the ultraviolet light, and they release the chlorine that can attack the ozone layer itself, chlorine and bromine atoms. And this was something that was predicted in the 1970s to happen on a very slow scale. But in the 1980s, this very dramatic depletion was discovered in Antarctica, and that's because there's a different kind of chemistry happening in Antarctica that nobody had really thought about. It's this heterogeneous chemistry on the surfaces of these ice clouds that form in very cold temperatures over Antarctica. And so the combination of this long-lived pollution and the particular chemistry and cold ice particles over Antarctica and sunlight altogether forms this ozone hole that has been happening every springtime, which in Antarctica is September, October, November, since the early 1980s. Okay, next question.
Okay, so Arundhati Kundu is asking that in your lecture, we have seen small and medium eruptions are also inducing forcing continuously, which is negative. So they have the ability to impose short-term climate change by helping to reduce global warming. But do they have any far-reaching consequences?
They can have consequences on the amount of heat in the ocean, which can last for a longer period of time. They eventually, though, the cooling that they induce will be overwhelmed by global warming from greenhouse gases. And so generally they're just a short-term effect. But if they're happening frequently enough, as they have happened over this period since 2005, then they can produce cooling that might be unexpected compared to the 10 years prior to that, when there weren't many of those. And so we need to understand their impacts in order to know why the Earth is warming at the rate that it is. Okay, next question.
So we don't have any more questions. So thank you, sir, for this wonderful discussion. We're really very fortunate to have you here. And we are going for a break now. At 10:30, the second lecture will be there. But for the participants, I'm informing that in the chat box, the attendance link for the attendance is given. You please fill up that link. And after a break of half an hour, half an hour, we'll come back, because the next lecture is scheduled at 10:30 a.m. So at 10:20 a.m. at least we must join. So for now, it's a short break. Thank you.
Yeah. So Dr. Mills, thank you so much for your this nice discussion. Yeah. So this is an informal discussion. People who wants to be here can be here. I will just hold him for a few more minutes. I guess. Is it okay, Dr. Mike?
Yes. Yes.
Yeah. So just I was thinking, as somebody was asking, that in small time scale, I mean, that volcanic eruptions of medium intensity is helping to, lower the temperature as a whole, I should say. So that is affecting, giving a negative forcing to the whole process of global warming. But it's volcanic area. Volcanic belt is very, limited. It's a specific region in the world which has these volcanoes. So, as a whole, in the global scale, what we expect actually? This is a local, almost a local thing, right? Not local in that sense, but in the volcanic belt.
Well, it depends really on the latitude of the eruption because of the circulation of the stratosphere. If you have an eruption like in the Philippines, Mount Pinatubo, or Mexico, Chichon in the tropics, you can have a good amount of material go into both the northern hemisphere and the southern hemisphere and have a global effect on cooling the planet. If you have eruptions at middle or high latitudes, because the air moves towards the poles in the stratosphere, it tends to stay in one hemisphere, in the same hemisphere where it happened. And so that would be more of a hemispheric impact on the climate. But yeah, since 2005, we've had significant eruptions in both hemispheres, as well as some in the tropics. But we still haven't had anything as big as what happened in 1991 with Mount Pinatubo, or 1982 with El Chichon.
Yeah, that's true. But if it reaches pole, then we have this another problem. If the temperature goes down there, then ozone hole can, pop up. So this is another point, I guess.
Yeah, and particularly it produces more particles, and you can have more chemistry happen in Antarctica.
Yeah. So if anyone wants to ask any more question, you can continue. Otherwise, I would like to thank Dr. Mikes to be here, spending one complete hour. It's night time for him, I guess, and then it's not office time; it's off time. So yeah, somebody is asking something. Can volcanic activity connected to El Nino La Nina? Is El Nino or La Nina getting stronger in intensity or frequency because of volcanic eruption?
This is a very interesting question, and there have been many papers looking at whether big eruptions have effects on producing El Niños or La Niñas. I would say the results are not entirely clear. It's very difficult with the limited number of eruptions, and also the confidence that we have in our Earth system models to really answer that question. But there are some studies that would indicate there is a connection, that eruptions can cause El Nino following it.
Sir, one more question is there from Shubhrajit. He's asking that can volcano activity connected to El Nino La Nina? And
yes,
is
Debolina,
El
I
Nino
have
and
already asked it. Debolina, I have already put that question. Yeah, we have already discussed this.
Yes.
Yeah. Anyone else wants to ask something else? Still, Dr. Mike is here. It's nice of him, but anyone else want to discuss anything? Now you can unmute and speak also if you wish. Anyone? I think no more question in the forum now. So yeah, somebody else is asking. Yeah. Yeah, so somebody wants to thank you. You can see the chat box also. Rocky Datta thanks you for this talk. Yeah, so I would like to thank you on behalf of all the participants and the organizer for being here with us. I know it will be not possible for you because time is odd tomorrow to be present in the valedictory session. I don't know. If possible, please be there. If it is not possible, I will not request you. Because all the experts, if they are available in the same platform, sometimes many discussions come up. So otherwise, thank you, sir. Thank you so much. I'll catch up later. Thank you.
Thank you for this opportunity. I will try to be there tomorrow as well.
Yeah. Okay. Thank you so much. Yeah. And our students may write to you. Sometimes don't feel disturbed. They want to know anything from you. They can communicate to you over mail.
Yes, I would like that.
Thank you.
Okay.
Bye.
Bye-bye.
Bye. So the participants, you can join back after some time.